You asked me uh, to explain this one more time, how this one corresponds to the loss of information. Do you agree?
Yeah.
Is that the question?
Yeah.
It is the question. So let's see. So the simplest example is the heads and tails example, right? So uh, if there are 10 tails and 0 heads, okay, then what is our ignorance? How ignorant are we? We are not ignorant, so 0, right? So whatever I plug in into this formula, it has to give me 0. Okay. What is my formula? So now I look at the probability of being at tails, which is 1. Probability of being at heads, 0. Then I take this formula, I do -1 ln 1 plus -0 ln 0. Of course, this one, if you take the limit, I think going from the right, probably it goes to 0. Does it? In our computational case, we will just make it 0. So do I get 0?
Yes.
Yes, I do. So now let's say I have 9 tails and 1 heads, right? You might remember that it suddenly increased our ignorance, right? Like there were 10 different places where that heads could be,
Yes.
right? So we are not looking at the 10 itself, we are looking at its logarithm. So what is the probability in this case? 0.9 and 0.1, right? Can you calculate this? Someone? Anyone? Well, MATLAB can calculate that, right? Times log 0.9 plus minus 0.1 times log 0.1. I get this number. So my ignorance indeed increased, right? When it would hit the maximum,
So 5
right? 1/2, right? 5 tails, 5 heads. Are you with me? So then I will have 2 times minus 0.5 times log 0.5. Do you agree? So that's 0.69. This is the maximum entropy that you can reach. So, but nothing is clear to you from your facial expression. I mean, 50%. You still have some entropy left to be maximized. So let me do that. Okay. So let's say I have what it has to do with energy and velocity. That's your question, actually, right? You can't see it. Yes. No, you can't see it. So let's say I have a room of particles and each one has the same velocity. Has the same speed. Okay. So in terms of energy, all particles has the same energy. What is that energy? mv squared over 2, right? So if I plot the probability of being at some energy with respect to energy, right? I will get a sharp line, something very sharp at mv squared over 2. And basically, this number will be, okay, it depends how I separate the rooms of energy. So let's say this is my dE, right? And this probability will be 1 over dE, because if I integrate, I have to get 1. Do you understand my point? Yes? What is the total entropy? The total entropy can be found by integrating minus P ln P of E at each E dE, right? Everybody with me? Yes? So what is this, what does this give me? Something very close to 0 or exactly 0? Something very close to 0. But you get the message, right?
Yeah.
Yes. So what will happen is that these particles will start bouncing, and we will get this Maxwell-Boltzmann distribution, which will maximize the entropy. Isn't this super awesome?
I see. So first they were like ordered.
You are very close to maximum entropy. I can see it in your face. Well, it means maximum ignorance, but in our case, it's whatever. You understand my point, right? Do you have any question?
No, but like if I were to make a comment, so
Yes.
let's say the probability of E is actually the fraction of particles at that energy, right? The probability is like number of molecules over total.
Yes.
Right? So if they all started sharing and colliding and everything, then there would be that at that point it would be incredibly difficult for us to figure out exactly what energy one particle has. Like in that head-tail case, we would not know where the tail was. But in this case, I'm trying to connect the analogy.
Why it will be incredibly difficult?
Because we don't know.
Yes, that's the point.
Yeah, that's what I'm saying.
Okay. You are giving a comment, yes, that. Okay. Perfect. So at the beginning, when I have this distribution, we know everything about every particle. By the way, there's a thing there that I'm not telling you, but that's the whole point. Today we will be really, really happy. Okay. So what is the point? We are looking at the energy. We are ignoring our ignorance in space. The particles are spread all over the place, and we know that we would have more information if they were at the corner of the room, same speed. So we will see today, for example, that if we look at just the energy distribution and find entropy, that will not be the all entropy that there is to find. It will be just the entropy because of the energy distribution. And again, you're coming back to your comment, since you know that there can only be one energy, you know that all particles that have that energy, you know everything about the system concerning the energy, but you don't know where they are. Let's say they are at the corner of the room, okay? Then you know everything about everything. Still not. You don't know what are the Vx's and Vy's. And we will step by step go from entropy due to the energy, entropy due to the speed, entropy due to the Vx and Vy, and ultimately entropy due to the velocities and the positions. That's the ultimate entropy. Of course, then there will be someone and he will say, what about the spin of the particles? Yes. Yes. We will hint to that too in a moment. Are you with me? Yes?
Can I ask something?
Yes, of course.
So that curve represents the increase in entropy, right? The one it's like
so let me quickly remind you, because you were not here.
No, I watched some of it, but I couldn't really understand what those axes represented.
Okay, so we actually did. Okay, over here we show that. Oh, sorry. Over here we show that we derive actually what has to be the probability distribution so that the entropy is maximum.
Yes.
right? That's the distribution that we get.
Alright.
So we know that when you hit the maximum entropy, you have a certain kind of distribution, which corresponds to what people call thermal equilibrium. Okay? Are you sure you get your answer?
Mostly, but the rest I could just compensate from myself.
I think today we will code every bit of it, so you will probably have much less entropy left. So, of course, we have to start with the system itself, right? So basically what we want to have a box with balls in it hitting each other like this. Do you see it? So let's watch it for a while. Do you think it's realistic enough?
Not bad.
Not bad.
That they are not losing energy.
They are not losing energy because microscopically,
It's elastic.
yes, it's elastic collision. So let's actually formulate everything step by step. So first of all, you need bouncing from the wall, right? So as I mentioned earlier,
We cannot see it.
perfect. As I mentioned earlier, it has to be like this. The particle has to hit the wall, right? Which means that, for example, the x coordinate of the particle has to be bigger than the L coordinate. This is x equals L minus d over 2, right? This d is the diameter of the particle. Do you agree? But for hitting the wall, it has to have one more thing. It has to be going towards the wall, which means that it has to have Vx bigger than 0. Yes? So what happens afterwards? X stays the same, but Vx will be Vx minus Vx. Sorry. Everybody understands this point? Yes? Good. Now, let me show you the place where we have, okay, so n will be for each coordinate bounce from the walls. Do you see this coded here? Do you see it, everybody? The line? So n represents, and if n is 1, it's x-axis. If n is 2, it's y-axis. So you can see that Vx, let's say, if it's bigger than 0, and if r is bigger than this one, then it will bounce. Do you have any questions with this line?
So why multiply velocity with
Yes. Okay. So this one will give me, if I run it, it will give me error. So why? Well, never mind. So if n is 1, then I'm talking about the x column of the velocities, right? So if they are bigger than 0, then it will give me logically 1, otherwise 0, right? So I'm doing an AND operation by multiplying, right? 1 times 1 will give me 1, otherwise I will get 0. Because I want both this logical operation and this. Why I'm doing this? Because MATLAB is good. MATLAB works fine when you avoid for loops, right? This is my way of avoiding for loops. Okay. Okay, very good. What about the elastic collisions themselves? So let's say I have to draw it big. Well, assume that they are equal size. Okay. So sorry about that. So this is the first particle. This is the second particle. and they have some. So if you are using vectors, life is much easier. So this is R1 vector, R2 vector, and let's say they had some velocities v1 and v2 beforehand. Okay, how will they collide? How I can find v prime? Obviously, they will be something like this, right? After the collision. How can I formulate this one? Are you interested in the derivation of this one at all? Or nah? Like,
We just state the principles. So that
okay.
so linear momentum balance, let's say, or something.
So what you do is you go into a reference frame. Are you still interested?
Okay,
No, I'm joking. No, it's interesting. You go into a reference frame that has center of mass velocity, which is v1 plus v2 over 2. Okay? Then you look at this system at that reference frame. Then you will see that there are actually two balls. So what is v1 minus v center of mass?
What do you mean?
I mean, formulate it. v1 minus v1 plus v2, right? Yeah, right? So it is v1 minus v2 over 2, right? What is v2 minus center of mass? See? It is minus v1 minus v2 over 2. So looking at it in a center of mass reference frame makes this velocity vectors exactly opposite. Okay? That way, you have this symmetry in a sense that this component of momentum and this component of momentum will cancel each other out. Okay? So the velocities will flip only in this direction. Do you understand my point? Yes? In that reference frame. I hope it's clear. Okay? So what is this vector? What is the length of this vector? Well, we need to find the projection of this one, this vector v1, for example, plus v2 over 2 on top of this one. So you need a dot product with r2 minus r1, right? Then the amount of this dot product should be added, twice of that should be subtracted from that. So basically you need to subtract from v1 minus v2 over 2, you need to subtract, or let me say, write it, v1 minus v center of mass minus v1 plus v2 over 2 dot product r2 minus r1 twice of this one, then you subtract twice of this one in the direction of r2 minus r1 unit vector. Okay? So, by the way, remember that we looked at it at a reference frame moving, right? So we need to add the center of mass velocity back after we are done, right? v1 prime then will be, so this one will go away. We will have only v1 minus v1 plus v2 dot product, la 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 la, right? So let's see where it's happening. It's so short here. This is our bounce. Okay? Of course, here also, as in the case of the collision with the wall, you need to be sure that the objects will collide, right? Are you following? I think this is also important, don't you think? Like this portion of whatever I'm telling you. Yes? I hope so. So how do you know that the two balls will collide? How would you know that? You need two things. Exactly. So the R2 minus R1 magnitude has to be smaller than the diameter. Do you agree? And the velocities has to the difference between the velocities has to have has to be aligned. Okay.
I think it should be negative on.
Yes, like exactly. The dot product has to be negative.
No, like V1 is this way, the other one is going the opposite direction.
So this one will collide, right?
Yep.
What about this one? I'm basically drawing the thing after the collision. But even if they are like this, they are not colliding, right? So what is the difference between these two? The difference is that if I add the minus of this one on top of this one, it will have projection on this vector, a positive projection. While if I add the minus of this one over here, it will not have a positive projection on this vector. So that those conditions so this is one of the conditions. So the norm of the vector has to be smaller than d. This is the other. Dot product has to be negative, as you said. Are you following? There is one more catch here, and I will explain it. It's not the best way to do it, but it's one of the simplest ways. So let's say I'm going to find who will collide with whom. Okay, so normally you need to compare everything with everything, which, thank you, which is, as you said, ridiculous. So you need to do n times n minus 1 over 2 operations or something like that, right? But what I could do is, what I'm doing actually is I'm sorting the x coordinates. So normally it's particle number 1, 2, 3, 4, 5. But I sort the x coordinates and I swipe the system from left to right. Okay, let's say I choose the first particle, the leftmost particle, and I look at the closest neighbors here while I'm swiping. If I am bigger than d, then there is no way for them to be neighbors. Okay, so I break the cycle. Then it goes from n squared down to n, order n algorithm, right? So I'm doing that over here. I sort the x coordinates. You can do it much better, I'm sure. There is. Can you sit like here so that I can see you too? Okay, thank you. So how do you search the space? You have trees for that, right? Well, that's much better, but I'm using this one, okay?
Sir, but what about
What about what?
two particles on top of each other with the same x?
That never happens. And that never happens. And even if that happens, still MATLAB will sort them in one way or another. And I'm not skipping any particle if they have equal x's. I'm just reordering them and going through that order. So no problem will occur with this algorithm.
And 3 body collisions are
Three-body collisions.
Three-part, that is dimension.
Good question. So what happens if I have something like this?
We cannot
Right.
see it.
What happens if I have something like this and the particle hits from here? What happens then?
So it's normally used in offices as a
Exactly. As a
decoration.
Newton something. They call it Newton something. Newton.
Last one will move.
Yes, the last one will go like this, right? Believe me or not, this algorithm has that property. I mean, I tried it.
Oh, you don't.
Do you want to see it now?
So, so what happens? They go inside each other. So right now they are not
Exactly.
black holes, right?
Exactly. So what happens is that, so there are time steps, right? At one time step, let's say this just collided with this one. So in the next time step, this will have zero velocity. This will have the velocity that had. Okay. Then in the next time step, it will move with sound velocity basically. So my dt will correspond to some kind of sound velocity inside these balls. I hope it is clear. So the next time step, this one will have zero velocity, and this one will have v velocity in this direction. Do you understand my point? No? So eventually, this one will pop out after the number of steps corresponding to the number of balls. I think it's a good enough approximation. And your question was, what happens if I have something like this? Right? Like this one just arrived. By the way, that never happens. Yeah, but let's say it happened. Then it will take care of it. Somehow. Let me think. I don't know. Yes, tell me.
No, I think you're right because our time steps are finite. So one collision has to take place before the other one.
Yeah,
So
okay.
it will sort itself.
Okay. So no problem.
But if it just hits them perfectly in the middle with full symmetry so that there is no time difference between the
No,
movements
it will just pass through them.
the other ones, then it could be an issue.
Okay. Actually, I think we would have problems if I used like some kind of memory for the velocities. Like at the beginning, I define, let's say, mv, memorize velocities equals v. Then over here, I find the new steps from that, etc. I don't do that, and it's actually something a little bit wrong, but nevertheless, it enables me to do each collision sequentially. Yes. So it at some point, so it will compare this one and this one. They will collide and come back. Well, it's too much detail, but
I understand. The thing is, here the code just analyzes the collisions as if there are two objects colliding, right?
yes.
But in very, very special circumstances, it could be something like two guys sticking to each other and one other one hits them on the middle, perfectly touching them at the same time.
It will just pass through because we're not coded for three. There are some
Yeah.
codes that pass right through.
It would just blow up, I guess.
Yes, I'm happy that you are so interested in this.
We see something mechanical.
Yes, me too. But it works fine from what we see, right?
Yeah.
Sometimes they get into each other too much, but that's okay.
Never happened, probably. Such a perfect
Let's see what happens when they are really dense.
There is always a time difference between the two and the other one. So,
That's a finite time.
Okay. Do you have any questions so far? Can we move to the next level? So did we go through all the points? I think we did. So this one basically draws those circles around, like with proper diameter, etc. Okay, let's see what happens if I start this system and if I look at the Boltzmann distribution, whether the particles reach the Boltzmann distribution or not. Okay? So let's start from the beginning, and let me tell you what everything means. So we start with initial conditions that are randomly so objects are randomly distributed inside the box. Okay? Then this is velocity, define initial velocities. Actually, it's too nice distribution because it's a Gaussian, and already so maybe we can make it bad distribution, or okay, let's do it this way.
Keep it all constant, the same speed for everything.
I hope I don't break the code. So basically this one, instead of having Gaussian distribution, we will have distribution between -1/2 and +1/2, a uniform distribution. Okay? Then I will explain what this means in a moment. So let's come to the energy part. So, by the way, I'm taking everything equal to 1. Everything that you see in thermodynamics, like masses of the particles 1, KB 1. What else do you see? No, temperature we will calculate. So basically, you calculate temperature. In this case, the energy of the system will be the sum of the mv squared over 2's. Since I take m1, then it's the sum of this one. Okay? What about the temperature? What is the temperature, how it is related to internal energy in thermodynamics?
I hate thermal.
You hate thermal. Today you will love it. Anyone?
There's the sum of the kinetic energies.
If I write 3/2 nkbt, will you agree? And what is this 3 here?
3 degrees of freedom.
Exactly, 3 degrees of freedom. Degrees of freedom. Okay. So, how many degrees of freedom do we have in this system? We have 2. So, what is a degree of freedom? It means that the particles, if they can move in 3 dimensions, then they have 3 degrees of freedom. If they also can rotate, then they have the 4th degrees of freedom, etc. Okay? So in this case, they are allowed to wander around in 2 dimensions. So you have 2 degrees of freedom. Are you following?
Isn't it 6? They can rotate around all axes.
Rotate? They cannot rotate. They are just
No.
they are
I
just
mean, you
spheres.
just said 4.
Ah, yes. What if they can only rotate in one direction? Anyways, thank you very much. So, so what is U in our system? Tell me.
The sum of the kinetic energies.
Yes, it's the sum of the kinetic energies, which is equal to, how many degrees of freedom do we have? 2 over 2 times n times 1, because we put k to 1, times t. So basically, the temperature can be expressed as 1 over n times v squares divided by 2. That's exactly, okay, this is the internal energy, okay, which gives you this formula. right? Where I define the temperature, it's over here. Do you see? Sum of all the velocity squares, right? Divided by 2, divided by n. Note that in 2D, CV equals 2. Are you following? Yes? Good. So, now that I have the energy of each particle, this gives me the energy, kinetic energy of each particle. Are you following? Do you see? Yes? Good. Now I want to find the number of particles between some bins. So this B energy means bins of energy. It will give me the numbers where I have, okay, basically I have some energy. Since I will do it numerically, I will have some maximum energy. I hope it's here. So I have some maximum energy. This is my maximum energy. But my bin is somewhere here. So I'm looking at a room over here which has D energy. So the width of it is D energy. And my bin is here, B energy. It's the bins. So these are the rooms. And this is 0. No. This is 0. So my bins are here. Do you understand? And this is, for example, D energy divided by 2. And this is also D energy divided by 2. So I will make a histogram of all the energies using these bins. Do you have any questions here? No? So basically this N energy are you lost? Almost lost. So I will I will look at Q times steps, which I call ensemble. And these are the number of energy rooms. So I will look at the first step, each room, how many particles are there in that room. Okay? In the next step, how many particles are there in each room. Okay? Then I will have a hotel that has Q floors, and each floor has the number of energy rooms. Okay? So I will get something like 5, 7, 6, I don't know, something like that. Then basically here I define a probability of energy, probability of being at some room. So basically I sum these hotel floors. So I get the sum down here. How many people are here? How many people are here? How many people are here? Are you following? Yes? Sorry. Okay, let's do this. Let's have a solution for this. Or not. So I will sum how many people are here. So I will get big number, right? I will get a distribution. But it has to be normalized. So I will normalize it by dividing each number with the total sum. Here I'm doing that. I sum all the floors. Then I sum the sum. I divide it by the sum of the sum. And I divide by D energy because I want to have this property PEDE equals 1. Are you following? No? Did you understand what I just did? That's good.
Yes.
Yes. Yes.
In that room, maybe each step, you mean how many particles are in each room, right? And then when you take the history, you sum it up for all of the steps.
Yes. Yes. Exactly. So you can see that I do it Q times. I'm looking at the moving average of everything. As I'm moving, I'm looking at moving average of Q steps. Okay. Then I define temperature, and I already mentioned it to you. Then what is the theoretical formula for the energy? Do you remember it? Exactly. It has to be e to the... This is Boltzmann distribution, right?
Would you switch to
This is the Boltzmann distribution. And in our case, it will be basically e to the minus e over k, e over t, because we take k equals 1. But there is also some coefficient in front of it. Instead of worrying about it, I will also sum whatever I get from this formula and divide it by dE. And I do it here. So this is the expression. This is divided by the sum of the expression, and again divided by the energy for normalization reasons. Did you follow? Yes? Do you have any question? So let's run it, and maybe we should run it actually slowly, because they thermalize so quickly. So this time I will not show you the balls themselves. Okay. Let me tell you what the problem is. We broke the code by... What if I do 3? Okay. Do you see? We started with a different distribution. The red one is the theoretical one. The blue one we are calculating numerically. Do you see how fast the system immediately goes to equilibrium, which maximizes the entropy? Everyone? Yes? Let's see it again. Yes? So, good. Now let's go. Do you need a break? You need a break. Okay. Let's have a break.